All right. Now I would like to consider the use of Gauss theory, given by the formula here. This is the mass, 4 pi gravitational constant, and in general, this is an integral of the gravitational field G and the dot product with the surface area element. So this integral is performed over a surface. And this Gauss way of solving problems is very efficient if the surface is symmetrical, like in the example here, it's a spherical surface. So let's solve the problem for a spherical shell. It's the blue one here, having mass capital M. And then we have two Gaussian closed surfaces around the shell. And for example, the external Gaussian surface, the black one here. Well, what is the mass inside such a spherical surface? Yeah, the only mass inside would be the blue one here, capital M. But if we instead choose another Gaussian surface like this one here, which is further inside, yeah, what is the mass inside that one? 0. There is no mass inside here. But inside that one, you obviously have the blue shell with mass M. So let's think about that you are standing in this point here, on that Gaussian surface, and later on this point. So if we start with that blue point over there, your mass is M. What is the gravitational field here? And this is what I'm treating here. If the radial distance is greater than the capital R distance to the shell, and yeah, here is R, capital R, and you're further away, so this must be greater than capital R. And I'm claiming that the gravitational field is in the negative radial direction. It's from that point, it's pointing downwards. Of course, if by symmetry, if you were here instead, it would be pointing in the negative radial direction. And also here, pointing like that. Here, it would be pointing like that, and so on, pointing towards the center. And in spherical coordinates, where you have a radial distance and a basis vector, ER, it can be expressed like this. The gravitational field is pointing in the negative direction of the radial vector to the point wherever we want to check it. So it will be like this, and the mass inside this Gaussian surface is obviously all the mass of the spherical shell. Isn't that inside? Yes, it is. So this is what I'm writing here. Okay, let us now consider a situation that you are now inside the spherical shell. For example, here or here or here or here or whatever. You are on a spherical Gaussian surface somewhere at the distance R, which must be less than the capital R distance to the massive shell. So what would the gravitational field, how would that be directed? Let's think about that. you would have interactions with all the mass elements on the blue shell. So for example, those here will give upward direction, forces upward, or if you like, G would be upward for those interactions. But then you have many interactions below too, so okay, it's maybe downwards then, or maybe perhaps a little bit to the right or to the left. I don't know. It is somehow to the left and right. I think, yeah, if there is an interaction here, it should be one here in the other direction. So okay, there should not be any forces along, let's say, the x direction. So it must be either below negative y direction or positive y direction. But I don't know for sure. So, okay, let's just say that the gravitational field is something plus minus, and GR is the field strength of the gravitational field. Directed, in this case here, either up or down. If I said you were here, it would be either in that direction or in that direction. So this is what we have. So, okay, let's use Gauss theorem for the enclosed mass. So if the radial distance is greater, the external Gaussian shell, yeah, okay, what mass is that enclosing? Yeah, all the mass. So all the mass is capital M. And that should be equal to this, yeah, and then integral. And what is the gravitational field for this case? Yeah, minus GR, ER, yeah, okay. And then the dot product with the area element, which is always directed away, outward direction from the surface. So, like this. So over here it would be directed like that, and here directed like that, whatever. And then that is just the area times the basis vector ER. So let's solve that. Now you see those minus sign, yeah, they cancel, okay. And GR on this surface, the field strength, it is the same here, everywhere. This point is not more special than a point here. So by symmetry, it must be the same field strength. So this is, when we integrate over the surface, this guy here is just going to be a constant. So we move that out from the integral. And then what we are left with is the unit vector dot this guy. But the unit vector dot this guy, that's 1. You know, ER dot ER equal 1. Or if you like, EX dot EX in the XY coordinate system, it's just 1. So you only have the integral dA. So what is that? That is summing all the small infinitesimal area elements over the whole spherical shell, and that is the total area, isn't it? And the total area of the spherical shell, what is that? 4 pi r squared. So, yeah, this is the result here, and then 4 pi, yeah, they cancel here. So what you get this, right? And what is that equivalent? This guy is equal to the capital M, so GR equal this. And if you like, the force, which is just mg, we have if we say we have a mass m, and here is g, we just calculated the field strength here, so we can find that the force is like this. So this looks like the standard gravitational law by Newton. So that's funny. So for if you're here and you have a spherical shell below you, it will just be the standard gravitational law where the distance is to the center of the shell, the radial distance. So That's a neat result. But now, let's continue. If you're here instead, inside the shell is the blue one here. So now you're inside, right? The distance is less than capital R. Well, so the mass inside here, what is that? 0. So we put the 0 here then. Okay, then this constant, and then integral of the gravitational field. But I was saying here that I don't really know if it's a plus or minus, but I know it's something here, it's some type of function, gr, and it will be in the ER direction along the basis vector here. But plus or minus, I have no idea. So let's just keep the plus minus here then, and then again, the dot product with the area element. But again, this point here is not special. It could be this, that, whatever. So when we're summing all the infinitesimal elements, the area elements, integrating over the surface, the gr here will never change. So this guy here doesn't change during the integration over the surface. So we can just move that guy out, okay? And then it's again dot er equal 1, and then integrating over dA, that will just be the surface area of the black one here. And now we consider that distance to be r, so it will be just 4 pi r squared. And then again, okay, minus times that, then minus like this, okay? But look at that, this expression here shall be 0 according to Gauss law. So, but the r is not 0, right? And g is not infinite. So there is only one solution, gr equals 0. So there is no gravitational field inside the blue spherical shell. So in fact, no matter where you are here, for example, this Gaussian surface, it doesn't matter where you are on the surface, it will be the same and the field will be 0. And we could have said that it was somewhere here instead, but it's the same thing. In every point inside the spherical shell, the gravitational field is 0, and also the force will be 0 then. So if you're inside, you will just practically floating around doing nothing. So that's the shell. And now let's change the shell to a continuous spherical body with, like the Earth, also with mass m. So then you will have mass inside here, right? Suppose now this blue circle here is the Earth surface, right? So you don't have mass outside that, but you will have mass inside the blue circle. Just like the Earth, a homogeneous body. So in case we are outside the Earth, like a satellite, it will be, the Newton's gravitational law will just be the same. Minus gmm over r squared. And we can put it in here. Nothing really changes if we're outside, and if that is a spherical shell or a spherical body, doesn't matter. So, but what happens if we are inside the Earth, right? What happens then if we are here? So, obviously, now you have mass above you, right, in here, and you're inside. You have mass around you, and you have also mass below you in this area here. So again, I don't know exactly the, if for those interactions maybe it's upwards, but for the interactions with all the mass inside, maybe downwards. But I know one thing, whatever the gravitational field is here, it will be the same in all these points because of the symmetry of the problem. So let's just again say, yeah, okay, so the gravitational field is somehow a function here, and by symmetry it's along the radial vector, either plus or minus. But remember, if you're here and the mass here, that's a shell, right? A spherical shell. And then we can take the next shell and the next and the next. So all the mass above you here, that is just the number of shells that we can add together, right? But we just proved that if you're inside a spherical shell, there is no G field, is it? And so for each shell, you can say, okay, there is no contribution to the gravitational field. And then, okay, next shell, again, no contribution. All the shells, zero contribution. So then we know a little bit more. So there is no contribution from the external shells. So in that case, the only thing you can have is interactions with the mass under you, right? So this part here. Okay, so then, all right, then we actually do know something, that G must be equal minus, like that, field strength and the basis vector. And we also know that the mass inside that Gaussian surface is not zero, because, well, it's a homogeneous body, so you have a mass inside that surface. So, okay, so I can't say zero here anymore, but let's say MR, all the mass up to radius R. So minus the constant, and then we put in that. This is dot product with the area. And again, this is for any point on the surface, this is the same field strength. So when we are integrating, you can move it out from the integral. Okay, like this. And then you have again ER dot ER, that's 1. And then the integral dA, but that's the area. So that's 4 pi r squared. And then like this. Okay, so this is the result then. And then we can, okay, so the gravitational field strength is G, the gravitational constant, times this mass divided by r squared. And this is the mass below. So you're here, and that's all the mass below you. Okay. And this is essentially what Newton's shell theorem says. The shells above you doesn't matter, and the only thing that does matter is the mass below you. So now we proved Newton's theorem using Gauss Law for mass. Rather, actually a quick proof here. So let's look a little bit further. The mass up to the radius R, that's volume times density. And for a spherical body, we know it's 4/3 pi r cubed. And if we take the whole Earth up to the capital R radius, then it's like this. So divide that by the total mass, you get this. So we now find the formula here, like that. Let's use that at the surface, the gravitational field strength, 9.81 meter per second square. That's gm capital R squared. Yeah, you can also see that here. This formula here is valid for up to just very close to R equal capital R. So yeah, that's it. And then let's see, what do we get? GR equal this, okay. G over R squared, that's that one. MR, what is that? It's this guy here. Yeah, okay, that's that. But G equal that. So G and then R squared, leave one R. So that's G. We have one capital R here, but then this divided by that is 1 R2. So you get this as a simple linear final result. So whatever, when R equal capital R, you get the same value as usual. This one here, good. And when we go down inside Earth, it will decrease. The strength here will decrease in a linear fashion. So what do we mean with that? Linear. Yeah, the radial distance here is, proportional to a constant G divided by capital R. Then it's a linear behavior. It would not be linear, for example, if it was R squared here instead. And the force inside the Earth is given by mg, like this, and so you get this. That's funny. If R equals capital R, you get the standard formula mg, and if R equals 0, so we are in the center of the Earth, then the force will be 0. And that, of course, can be understood also, because if you're over here, you will be interacting upwards here and downwards here, and any force here, when we sum them all, they will cancel each other. So the force, of course, must be 0 in the center. So now you learn something about the Gaussian law in classical mechanics. So thank you for listening. See you later. Bye-bye.